Good morning, everybody. Welcome to part 3 of this thermochemistry unit. The topics that we're going to look at today are heat of solution and calorimetry. So heat of solution means when you dissolve something in something else, which is something we covered in our last unit, what kind of a heat change is associated. Everything that you dissolve in any other solvent, there will be some kind of a heat change associated. Some are endothermic, some are exothermic. And calorimetry is the transfer of heat from one thing to another and actually measuring it. So we're going to look at those two topics. We're going to do things a little differently today because I'm actually not going to use a PowerPoint presentation much at all. In fact, what I'm going to use instead is I want you to have this note sheet in front of you. Okay, so these are the notes for part 3 of thermochemistry, and I'm actually going to do some demos with you. All right, so let me switch over to my camera here. Okay, hello. Welcome to my kitchen. All right, this is the best I can do for a sort of chem lab. All right, so for demo number 1, what I have here is I have measured out 100 grams of water. The demo says a styrofoam cup. I didn't have a styrofoam cup, so I have a plastic cup here, okay? And what I'm going to do first with my thermometer here is I'm going to measure the temperature of just this room temperature water. So on your note sheet, I want you to record right in the very first blank where it says initial temperature. This water is reading 22.6 degrees Celsius. Okay? What I'm going to add to this water is 10 grams of calcium chloride, which is just a white powder. No, it's not cocaine. All right? And so what I'm going to do is I'm going to, you can see it right here, I'm going to pour this into the water. It's going to dissolve, and I'm going to measure the temperature change. Does it get cold? Does it get hot? And we're going to record, if you look on your note sheet where it says final temperature, we're going to record what either the lowest temperature it reaches or the highest, depending on what happens. So here we go. So I'm adding it, and I'm going to use my thermometer to stir. And it just kind of forms this cloudy solution, and I can see right now that it is going up. Okay, it is getting warmer. Pretty significantly, actually. I'm stirring, and it happens pretty quickly. It's into the 30s, and let's see, is it going to keep going up? And now it's going back down. Okay, so the highest temperature that this reached was, let's write it down, 38.5 degrees. Okay, now let's think about it. It got warm. Okay, I can feel it on my hands here. It's a little bit warm. What kind of reactions feel warm? Exothermic. All right? Heat is released from exothermic. The reaction is going on in here. Heat is exiting, leaving the system being what's in the cup, and it feels warm to my hands. Okay? So let me come back to this, the note sheet here. All right, and let's fill some things in here. Let me change colors. Okay, so our initial temperature was 22.6 degrees, and the final temperature was, I think I said 38.5. Okay. Now the mass of the water, all right, was 100 grams. I measured out the mass of the calcium chloride. That was 10 grams. So come back over here. The total mass of the whole solution would then be 110 grams. Okay, so I'm going to, ask you to pause the video at certain points. All right, I want you to use your periodic table to convert 10 grams of calcium chloride into moles. So pause now. I'm going to go ahead and enter it. Okay. Now it says determine the heat flow using the formula Q reaction equals negative MCAT. Okay, that's what I call it, the MCAT equation. So essentially what this is saying is that the heat, remember Q means heat, of the reaction is going to be equal but opposite in sign to what's going on in the solution. Think about the solution as like me measuring the temperature of the water. Okay, it's almost like the calcium chloride is the reaction on the left-hand side there of Q reaction, and the water is what's on the product side, or the right-hand side, excuse me. All right, so let's write this out. So Q reaction equals negative. The solution had a total mass of 110. Okay, I want you guys to assume, and if this were a test question, I would definitely tell you, we're going to assume that the specific heat capacity of the solution is the same as that of pure water. Okay, and then we're going to do final minus initial. Okay, I'm going to plug that into my calculator and I get this number. 7317.8, and that's in units of joules. I'm going to just go ahead and convert that to kilojoules just to make kind of a nicer number. And I'm going to put a box around it. Okay, so what this is saying is that the heat of solution for calcium chloride is negative 7.32 kilojoules. It's negative. Exothermic reactions have negative heat values. Okay, and that makes sense. That jives with what I felt. It felt hot. That's definitely an exothermic reaction. Okay, so actually we can go ahead and come down to this last question here. It was definitely exo. All right. This one in the middle here where it says determine the heat of solution in kilojoules per mole, that's only because that is typically the units. That's typically the way that heats of solution are expressed in units of kilojoules per mole of the thing dissolving. Okay, so negative 7.32 kilojoules. And look back up at the top. How many moles of calcium chloride did we have? 0.090. And when we divide that out, I get this. Okay. So this is a little different because we have, it doesn't seem like there's two parts to this situation, but there sort of are. there's like the solute itself, and that's sort of the heat of the reaction. And then you can think of the water and as sort of the other part to this. So the dissolving released heat and the water absorbed it. Okay, released and absorbed are opposite in sign. That's why that negative is in that formula. Okay, so the heat of the reaction is equal but opposite in sign to what's happening to the solution or the water. Okay, so let me clear this out, and we're going to do a second demo. Okay, so let's scroll down to the next one. All right, let me come back to my camera, back to my wonderful kitchen here. All right, so demo number 2. Same kind of cup. Okay, I've again got 100 grams of water in there. This time I'm going to be adding 10 grams of sodium nitrate. Okay, but before I do that, let's record the initial temperature of just the water before I put anything in it. And again, it should be very close to the temperature of the other sample of water that's just at room temperature. Looks like this one's a little colder. Let's call it 21.9. Okay, so 21.9, this one's a little cooler than my other sample. Okay, now again, this is sodium nitrate. Okay, yes, I know these are measuring spoons. Shouldn't have chemicals in them, but everything's a chemical. Anyway, sodium nitrate is another just white powder. All right, and I'm going to add it. I'm going to use my thermometer as a stirring rod again, and I'm going to measure the temperature. It may go up, it may go down. We'll have to see. Okay, so here we go. I added it, and I'm going to stir it up here. Okay, and I can see that it is dropping in temperature. So this one, instead of heating up, this one is getting cooler. And let's see how far this one's going to go. Not quite as fast. I mean, it is fast, but it's not going as far as the other one. Okay, and it's already going back up. Okay, so 16.7 is the lowest that this one got. So it got a little cooler. That's the opposite. All right. So this one is not exothermic, it's endothermic. All right, let's come back over to the worksheet here. All right, and let's start filling some things in. All right, we said the initial temperature was 21.9, and the lowest that it got was 16.7. Okay, I once again had 100 grams of water. The sodium nitrate, I had 10 grams. So once again, we've got 110 grams total. Okay, pause the video if you want. I want you guys to convert sodium nitrate, those 10 grams. Use your periodic table. Let's convert that to moles. Okay, and now we're going to do the exact same thing, just with different values this time. So the heat of the reaction is equal but opposite in sign. We're going to assume that the specific heat capacity is approximately the same as pure water, which it would be pretty close. It's a good enough approximation. Okay, and we're going to do final minus initial. Minus 21.9. Right, I'm going to plug all that in. And this is what I get, 2393.2, and that's in joules. I'm going to change that into kilojoules. Okay, put a box around it. So this one came out to have a positive value, and it should. It got colder, okay? Heat is absorbed. Now, where would that heat be coming from? From the environment, from the surroundings. All right, remember something I said in the first lesson is when you touch something and it feels cold, it's not necessarily because it is cold. I mean, it might be, but it also could just be that it's cooler than your hand, which means heat is being absorbed from your hand. And if your hand is losing heat, then it's going to feel cold. All right. So this particular solute has an endothermic. I'm going to go ahead and circle it. Endothermic heat of solution. Okay, our last step here is let's just convert this into units that we typically see for heats of solution. And we already found those moles. And here we go. Okay. All right. So we've done 2 demos. The last one is a little different. All right. So if you scroll down, all right, this one is a little odd. All right, let me come back to my camera here. Okay, so new cup of water. Okay, this cup of water, if you look at demo 3, I've added a little bit more water to this one. This has 150 grams of water in it. And I'm going to add a rock. Yes, that's right, just a rock that I found outside that I have been heating in my oven. Okay, I've set the oven to 200 degrees. It's been sitting in there for a while. So I'm going to assume that the temperature of the rock, and that's one of the things to fill out here under demo 3, initial temperature of the rock, since it's been in a 200 degree oven for a while, I'm going to assume that it's at 200. Okay, actually before I pull it out, let's take the initial temperature of the water. Again, it's just been sitting out here on the counter, so it should be pretty close to the temperatures, the initial temperatures of the other 2 waters. And let's see. Right on the dot. Okay, 22.0. 22.0 degrees Celsius is the initial temperature of the water. Okay. Now, before I pull the rock out of the oven, what I'm going to do is I'm going to add it to the water. And I want you guys to kind of think about this for a second. The rock is very hot. The water is at room temperature. So what's going to happen to the temperature of the rock as soon as I put it in there? It's going to go down, right? This rock is going to cool down. What's going to happen to the temperature of the water? It's going to heat up. And when is that process going to stop? When those 2 reach the same final temperature. Okay? And that's, you'll see, that's one of the data points that we're going to record where it says final temperature. That'll be the final temperature of both of them. Okay? Now again, before I pour the rock out, let me ask you one other thing. What is happening to the rock? We know it's going to be cooling down. Does that mean that the rock is losing heat, releasing, or is it absorbing? The rock is going to be releasing heat. So what must the water be doing? Absorbing that heat. Okay? And that's what calorimetry is. We're going to actually put some math to this. One thing is losing heat, the other thing is gaining it, and those are equal. All right, let me just show you guys something for a second. There is just a real simple formula here, okay? When you bring two things in contact with each other that are at different temperatures, one thing, the hotter thing will lose heat, the cooler thing will gain it. The amount of heat lost and gained are the same, but they're opposite in sign, because the thing on the left is exo, it's negative. Heat gained is positive. How do you make -4 equal +4? You throw a negative sign in there. Okay? So let's do this demo, okay? 200 isn't that hot, but I don't want to burn myself, you know. Okay. So just so you guys can see this. Okay, just just an ordinary rock. All right. So I'm going to put the rock in the water, and then I'm going to measure the temperature. Oh, okay, here we go. Okay, the water's definitely heating up. Okay. And if you're wondering, what are we trying to solve here? We are going to solve for the specific heat capacity of this rock. Okay, now of course, depending on what rock I pick up from outside, every rock is going to be a little bit different. Every rock is going to have its own unique specific heat capacity. Okay, so the temperature's still going up. Okay, we're into the 40s at this point. It started at, 22 degrees on the dot, and it's in the 40s. It's kind of slowing down though, and I think okay, now it's going back down. Okay, so record this number, 45.8 degrees Celsius. That's the highest that it got. I actually thought it would go a little higher than that, but that's okay. All right. So let's come back over to this worksheet and start filling some information in. Okay, so what do we know? Since the rock was in the oven for a long time, we're going to assume that the rock was at 200 degrees. We measured the water, which was exactly 22. Okay, and the final temperature, 45.8, I think that's what I said. Okay, the mass of the water was 150 this time. And I should have told you this ahead of time, I did mass the rock before I had put it in the water. Okay, and the rock came out to have a mass of 117.1 grams. Okay, so before we get to any of the math, which part of this situation, the water or the rock, which one was absorbing heat? Okay, that's which one was endo? The water. Which part was losing heat, releasing it? The rock. Okay, so look at what it says here. Use the formula MCAT of water is equal but opposite in sign to the MCAT for the rock. We're going to use that to determine the specific heat capacity for the rock. So the C, the variable C on the right-hand side, that is the only part of this that I don't know. That's my only unknown. So let's fill in what we've got. 150 grams of water. Water's specific heat capacity is 4.184. And water's temperature, final minus initial, 45.8 minus 22.0 equal but opposite in sign to the mass of the rock I don't know the specific heat capacity of it. That's my unknown. Final minus initial. Okay. So what I'm asking you to do is solve for C. All right? And so if you want to pause the video and take a second and come back, and I'm going to put up the answer, you can check and see if you got it right. So here's the specific heat capacity for our rock, and here are the units for specific heat capacity. Final answer. Okay? And so guys, this process that I just performed, this is called calorimetry. Okay? It's, finding some unknown piece of information based on heat changes. All right? There's another question that I want to work through with you, okay, before I wrap this up. If you look over on the second page of these notes, there is question number 2. I'm going to come to a blank screen here. Let's erase that. Okay, I want to look at question number 2. Question number 2 has a very similar situation to what we just did with the rock. It says, a gold ring that weighs 3.81 grams is heated to 84 degrees and is placed in 50 grams of water at 22.1 degrees. What is the final temperature? I don't know if you all can hear my cat meowing. Okay, so this is question number 2. All right, now, before we do any math, I want you guys to understand this conceptually. I don't want you to just be blind number crunchers. The ring is at 84 degrees. It's hot. The water is at 22.1 degrees. So the ring is hot, the water is cool. Think about what's going to happen here. The ring is going to lose heat, and the water is going to gain it. All right, but it's going to be the same setup. So I'm going to write it out. So the heat associated with the change for the gold ring is going to be equal but opposite in sign to the heat change associated with the water. And by the way, guys, when you're doing these calorimetry problems, it does not matter which side you put the negative on. As long as you put it somewhere, it's fine. So we're going to do an MCAT equals negative MCAT. This is the mass of the gold ring. There's a chart right above this question that gives me the specific heat capacity for gold. Okay, now, what is the final temperature? That I don't know. That is my unknown. I'm going to call it TF. T final minus the gold was at an initial temperature of 84. Okay, is equal but opposite. All right, the mass of the water was 50 grams, 4.184. My cat is meowing like crazy. Okay, now again, I don't know the final temperature, but guys, guess what? It's the same final temperature. Remember, the gold and the water are going to end up at the same final temperature, so I can use the same variable. Minus 22.1. Okay, now what I would recommend at this point is pause the video, because this is a bit of an algebra nightmare. Solving for TF. I want you to take some time, pause the video and solve for TF, and then unpause it when you're ready. So if you did your algebra right, this is the final temperature. Okay, now, I want you to notice something about that temperature. What was the initial temperature of the water? It was 22.1. The water only went up by 1/10 of a degree. Now, the ring changed temperature pretty dramatically, but the water didn't. And I want you guys to understand that conceptually. Remember, in the first lesson, we talked about how metals are excellent conductors, okay, of heat. They absorb heat very well. They also release it very well. Gold, metals, all kinds of metals cool down rapidly. And we can see that this gold, that happened. Water, which has a high specific heat capacity, does not heat up and cool down very well. It's very difficult to do that. And I can see that happened. Putting this very hot gold ring only caused the water to go up by 1/10 of a degree. Okay, because water has such a high specific heat capacity. Okay. So that's a calorimetry problem, and I just wanted to go through that one with you. So I hoped you've enjoyed getting to see a little bit of a snippet into, my kitchen. So anyway, I look forward to seeing you guys in our next lesson. Take care.